Okay, let's go ahead and get started for the day. Today, we're going to continue where we left off last time. And we're going to focus on, we talked about concurrency last time and how it could be difficult to debug and how it could be dangerous because problems, concurrent problems that stem from concurrency's non-determinism can end up not showing up during testing, and then when you actually put the system out in the field, you could get really unlucky and get one of those concurrency flaws that then you get a bad ordering, it shows up, and then you see suddenly you have this catastrophic failure, or you get the wrong result from something. And we talked about some real-world cases where that happened. We talked about the V-22 Osprey vertical takeoff crash that killed people. We talked about the Therac system that exposed people to high levels of radiation, which killed people. We talked about the blackout, Mars Pathfinder. There are a number of things we talked about there. But today we're going to look at some code that actually has a legitimate problem. All right, so quick thing, overview of what we're going to do today. We're going to review that CSP model of concurrency. We're going to look at a concurrent example, analyze that example for that potentially dangerous behavior if we get unlucky when we're running it, and then we're going to attempt to find a solution to that problem. We're going to finish up, not to have a plot spoiler here, we're going to finish up with a couple of solutions to that problem that we see in that example. So let's go and get started. So first off, let's review the concurrency operator, or the concurrent with operator. If we have two processes, A and B, and those are both sequential. And what that means to be sequential, they're fully ordered. So A has a list of instructions that it goes through, instruction 1, instruction 2, instruction 3, instruction 4, until it gets to the end. B has the same thing. Those are fully ordered. In other words, parts of A don't overlap other parts of A. They run one at a time. Even if there's a loop, it's still sequential. And parts of B don't overlap with other parts of B. They're completely sequential. But what the concurrency operator means, as we show here, A concurrent with B, that means that those two processes may overlap, that they're concurrent with one another. That means that's okay for them to overlap their execution. And the formal definition of that, which we saw last time, was there exists some legal execution such that A does not come before B and B does not come before A. And if you think about what that means, the only way that it could be that A doesn't come before B and B doesn't come before A, the only way that that could happen is if they overlap in some way. Could be like this, could be like that, could be like that, could be like that, could be anywhere in between those extremes. But there exists some legal execution where they're allowed to overlap. Now, another way to think about that is A is concurrent with B if and only if there exists some valid execution such that they are allowed to overlap each other. One thing to note, it just says there exists some. It doesn't say they're obliged to overlap or they're forced to overlap. It just says it's okay for them to overlap. And a quick review of the CSP model, which is concurrent sequential processes or communicating sequential processes. Each process itself is sequential. The processes may overlap execution, but they're not forced to. They're not obligated to overlap. And we also don't make any timing assumptions about them. So in other words, A concurrent B, if we have sequential process A that looks like this and B that looks like that, when we say they're concurrent, it doesn't mean that A1 and B1 will run at the same time and A2 and B2 will run at the same time and A3 and B3. It doesn't mean they work through in sync. It basically just means it's okay if they kind of overlap each other in some way. And kind of to finish up that review, if they are concurrent, we have these two sequential processes, and if they're allowed to overlap, that has some implications. That means there are a whole bunch of possible effective orderings that we could that could be exhibited. And that also means that execution is no longer deterministic. In other words, A concurrent B, what's the first thing to happen? Well, it might be A1, it might be B1. We don't really know which one. It could be one or the other. And then after it picks one of those, what's the next thing that could happen? Well, we don't know. So when we say effective ordering, we might say, what are all the possible ways we could interleave the instructions from A and instructions from B? And really, there's a large number of those. So that means that execution is no longer deterministic. It will be one of those possible orderings that happens anytime we run the program. But we don't know which one. And the next time I run those two processes concurrently, it might be a different ordering. Now, next time, it might be a different ordering. And there can be a whole lot of those different possible orderings, especially when we get to a larger number of processes or processes that have more than 3 instructions each, like we show here. So some effective orderings might lead to different results or incorrect results. Some of them might lead to problems where the system locks up or something like that. And all of that stems from the non-determinism. So testing, since when you test it, we're just getting an ordering. We're not getting all the orderings. And in some cases, it might be impossible to test all of the orderings because there might be so many of them that we wouldn't have enough time to test all of them. We don't know which one we're getting when we run the program. So that makes testing concurrent programs difficult. It makes them maybe a little bit, quite a bit more complex when something goes wrong because you run the program and something crashes. How do you know what ordering you got that caused that? You have to analyze the code. So that's why it's good to be proactive and understand the kinds of things that cause problems when we have concurrency and essentially address it as we're creating the system as part of our design. Now, we also might have more than 2 concurrent processes. Instead of just A and B, we might have A, B, C, D, and they might have different numbers of instructions. Like A and B might only have 3, C might have 20 instructions, D might have 50 instructions at this kind of lower atomic level like this. All right, so the CSP model of concurrency, that model thus far looks like this. We have a set of processes, has to be 2 or more to be concurrent. You can't have one process be concurrent with itself. So we have a set of processes. Each process itself is sequential. No assumption is made about the execution speed of the processes or the timing of their execution. But we know since they're concurrent that they may overlap their execution. And that means with them overlapping, there are effective orders of execution. There are a variety of them. It can't be determined ahead of time. And there might be a very large number of them that are possible. Even with just these 2 little things like this, there are 20 possible effective orders of execution with just 2 processes with 3 instructions each. And if we make those 4 instructions each, it's even larger, and it kind of grows very rapidly. So that means that execution is non-deterministic. We're going to get one of the orderings, but we can't predict which one. Some may be more probable than others based on the timing of the code and the way the system runs, but we can't predict which of the orderings we're going to get. So that non-determinism and all of those possible orderings could present problems. So potential concurrency dangers. And the reason why this can be dangerous is that most orderings might be safe and valid. Some, maybe even just one or a few or a handful or a small number, might prove problematic. And the problematic orderings might be rare. We might never see them show up during testing, but once we deploy the solution, we send the rover to Mars, suddenly one of them shows up and the rover locks up. Or we test it in our office and everything works, and we send it out to perform radiation therapy on patients, and it starts killing people. And so testing, when you deal with concurrency, we have to be careful, not just write something and then test it and say, hey, it worked, so it's good to go. Sequential programs, you can do a little bit better job testing like that. You can run the code. If it works, it works. If you work and run it on all the different input possibilities, you say it's good to go. Concurrent programs, though, you give it one input possibility and you run it, it works. It might not always work, so that's why we have to deal with that. So the idea is we can't eliminate the so how do we deal with that? What do we do to solve those dangerous situations? Well, the first thing is we can't eliminate the non-deterministic execution, or the system's no longer concurrent. Well, that might be a solution. You might say, okay, I have this concurrent solution. How can I make it into a single-threaded or single sequential program instead of using a concurrent solution? That might be a solution, but then it's no longer a solution to concurrency because we're just getting rid of concurrency. That's like saying, how do you solve world hunger, well, you kill everybody on the world, there's not any hunger anymore. That's not a good solution. Well, it would technically be true. It would not solve the problem. How do we get rid of the dangers of concurrency? Well, you could say get rid of concurrency. It'd be not really eliminating the dangers as much as eliminating the entire thing. All right, the second one here, and what we're going to focus on today at least a little bit, and we're going to do this a lot throughout the semester, is we need to find a way to preserve concurrent execution. So allow the processes to be concurrent with one another, but find a way to avoid those bad execution ordering somehow. Find a way to make our code such that it's written in a way that the bad orderings can never happen. We can't get dangerous behavior out of it. All right, so let's look at an example of what we're talking about here, an example of one of these problems, because so far it's been more just abstract. And the thing that I want to look at is, or we're going to start with, is this problem that's often in the literature referred to as the ornamental garden problem. And the idea here is, let's say we have a city, and it's got this beautiful ornamental garden that has hedges and, I don't know, it might have a little labyrinth of bushes that you can walk through. It might have a rose garden area and benches to sit on and enjoy the nice weather. You could go have a picnic there maybe, but it's only open during daylight hours. They close it down at night to prevent vandalism and other problems, loitering. So to control the access to it, they put a fence around the garden. It's fenced or walled in, and they have two turnstiles they install, one at the entrance and one at the exit. So they have these two ways in. So the turnstiles and gates are to be locked at night once the garden is closed. And they don't want to accidentally lock anybody inside, so they set up a system that keeps track of the number of people that come in and the number of people that go out. And so the idea is somebody comes in, they click through the turnstile, it goes tick, and when it ticks, a counter goes up to 1. It says one person inside. That person can walk around the garden. Another person can come in, tick the turnstile, the count goes to 2. But when somebody leaves on the other end of the garden, they go out the exit turnstile. That one ticking makes the count go back down. So where it was 1, 2, now it goes back to 1. The other person leaves, it goes back down to 0. And this is essentially the garden's way of making sure nobody's left inside. So at the end of the day, before they lock the gates, they look at the count. If it says 0, they lock the gates. Everything's good. Everybody who came in also left. If it says there's one person inside, they have to do a security sweep or make an announcement or something like that and make sure everybody's out before they can lock the gates. So here's what the system might look like. So here's a little picture that I made that shows that. So here's the garden grounds. Here's the entrance turnstile. You walk in, that rotates. You spend your time looking at things and enjoying the nice garden. And then you walk out the other exit, and that ticks. And then it counts you as coming in. It counts you as going out. And some of you may have experienced something like this going into stores recently with the pandemic going on, where there's somebody at the door counting how many people are in, and if it gets above a certain number, they say you got to wait, the occupancy is too high. Wait until somebody leaves, and then you can go in. But that's what we're talking about, is keeping track of how many people are currently inside of here. So here's what the code might look like. You have some main that starts up, count equals 0, and then after that, when, let's say these processes now are running concurrently, but let's say they're running on an interrupt. So when somebody comes in, click, the inner gate code runs, count equal count plus 1. When somebody exits, click, this code runs, count equal count minus 1. Since that's a global variable that's shared, we have one single count variable that starts at 0. As people come in, it goes up. As people go out, it goes down. So the count variable is a shared global. The gates can click at any time because it's just whenever people click them. And their code executes concurrently. In other words, this and this are running concurrently with one another. So it looks very simple. And if you look at the code, this makes total sense. Somebody comes in, we add 1. Somebody goes out, we subtract 1. We started at 0. At any point in time we want to look at the count, we read that global variable count. The number it tells us is how many people are in there. So looks simple, makes sense. What could possibly go wrong with a setup like this? Seems very simple. You look at the code. But here's the problem. They install the system. It seems to work great. And then one night, somebody gets locked inside overnight. They come in the morning and a person is in there and they're like curled up and they're cold and they're crying and like, why did you lock me in? And they said, well, the count said 0. And then a few days later, at the end of the day, the system reports 5 people inside, but security sweep doesn't find anybody. So it reports that there are 5 people inside. And then maybe a week later, they come and the system reports there's -1 person inside. So one more person left than came in. So did the garden like magically grow or spawn a person at a spawn point? No, there's got to be something wrong with the system. So the engineers might go back and look at the turnstile hardware, try to figure it out and say, all that seems fine. And they go back and look at the code we had over here and they say, okay, count equal count plus 1, count equal count minus 1. That all looks fine. How could that go wrong? But the problem here with this is that those lines of code can run concurrently. So let's break that down and look at where the problem is. So the problem here is the shared global variable count. And why is that a problem? Both processes are updating the same variable and they're updating it concurrently. So let's break down the operations of those variable updates. So if you look at a line of code like this, count equal count plus 1, or even count plus equal 1, or count plus plus, eventually you boil that down to inside the processor, it's got to pick up the count variable value from memory, add 1 to it, and then stick that back into memory. So that's what the processor has to do. So if you were to look at the machine code of that, it might say pick up the count variable, put it in a register, add 1 to that register, and then store it back into the variable. So in other words, read the count, modify the variable, store it back into memory. That has to happen in those multiple steps. Fetch the data, modify it, restore it. And that's happening on both the entry gate and the exit gate. So process B is doing the same thing. It's just subtracting when it modifies it rather than adding when it modifies it. Okay, so why is that a problem? That doesn't seem like that should be a problem. So I'm going to give you a couple minutes here, at least a few seconds to look at that. And if you want, you can pause the video here and look at that and see if you can think about how that could go wrong. Remember, this is like process A, where you have A1, A2, and A3, and then process B, where you have B1, B2, and B3. And so notice that if all of A happens before B, or all of B happens before A, that's fine. But with these being concurrent, it says they're allowed to overlap. So you can get effective orderings where they're interleaved in a variety of different ways here. And so see if you can pause the video, look at this part of the code, and see if you can figure out one of those orderings where things can go wrong. Okay, well, hopefully you actually paused the video instead of just staring at me in silence for a couple seconds. But let's go ahead and take a look at that. All right, so here are the two processes in their kind of assembly language form: read, modify, store, read, modify, store of that same shared variable. So you might say, is the problem that both processes are using the same register of the processor? And you might think that, but realistically behind the scenes, if this is an interrupt, we're going to push the registers, use them, and then pop them to restore them to the state they were in. So probably not. That's probably okay. But a developer might look at that and go, oh, I know what the problem is. These are both trying to use the same AX registers. They might try to fix that. And they might change it to, let's use a different register in there. We wrote it in assembly language or machine code or whatever. We change it so we're sure it's using a different register now. Now we think we've fixed the problem. But the system fails again. And it fails only sometimes. It works most of the time. Every once in a while, somebody gets locked in overnight. Or every once in a while, we get more people leaving than have entered. So it fails, but only sometimes and randomly, even if we are using different registers like this. So the question is why? Why is this happening? How is it possible that some code that's so simple with so few instructions and such a simple idea, add 1 to count when somebody comes in, take 1 away from the count when somebody leaves, how can that go wrong? And again, the problem isn't the register like that. The problem here is that shared update of that variable count. So let's look at how that can fail. So let's look at how it can fail. Let's say the count is equal to 20. There are 20 people in the garden. and someone comes in just as someone is leaving. So the count should remain 20, and most of the time when we run this, we would get 20. So in other words, we have 20 people. Somebody came in, which would make it 21. Somebody's leaving, which would make it back to 20. Or somebody leaves first, goes to 19. The next person comes in and goes to 20. And anyway, if we're at 20 and someone comes in and someone leaves, after that, we should have still 20. But when we look at that system in practice, we could end up getting either 19 or 21 or 20. Most of the time we would get 20, but we could get 19 or 21 sometimes. So let's take a look at the problem sequence that causes that. All right, so here's a problem sequence that causes that. So A1 runs. So A1 is the read. But before A2 and A3 can run and modify and restore it, B1 runs and picks up the same 20. So they've both picked up the same value of 20. Now they both do now A finishes, it modifies it, adds 1, gets 21, restores it, so it put 21 back into memory. But now B runs, and B had, remember, picked up 20, it subtracts 1 to get 19, and it restores 19. So the final result is 19. So this whole add that happened here and restore was completely overwritten by B running. So the entry event got completely lost. The code ran, but the result of it doing that got lost because they both picked up 20. One of them came up with 19, one of them came up with 21. The 21 got written first, the 19 overwrote it. We lost the increment there. Now, let's look at another one where it loses the 19. It's kind of the same process. So A and B, A1 and B1 both pick up the 20 that's there originally. A2 then runs and adds. B2 then runs and gets the 19. B3 then restores the 19. A3 puts a 21. Now we've lost the one leaving. So the exit was lost in that case. So go ahead and, if you need to, pause it here. Take a look at that. Wrap your mind around what's happening there. And then think about, are there other possible orderings here that can also fail? And the answer is yes, a lot of them. But as long as A reads, modifies, and stores and isn't interrupted by B, isn't interleaved with B, or as long as B reads, modifies, stores before A, we're good. And that's going to happen most of the time in this garden because this is relatively simple code and it's going to run relatively quickly. So most of the time somebody comes in, pick it up, change it, restore it. Somebody leaves, pick it up, change it, restore it. Most of the time it's going to be unlikely that somebody's coming in at the exact time that somebody's leaving and those two things interleave each other in some way. So most of the time this is going to work. But there's the possibility, because these are concurrent, that we end up with this corrupted thing and some of the entries get lost. So once the value is read, it's important that it's updated and then stored before another one reads it, or we risk losing one of the operations. And that section of code that's updating, reading something, modifying it, and then updating it, or that cannot be overlapped with something else, is called a critical section. A critical section is a section that it's important, critical, that once it starts, it completes without being disturbed. So in other words, these two processes, these 3 lines in each of these, are critical sections with respect to one another. In other words, once I start and pick this up, I can't let anyone else pick that up until I'm done with it. Okay, so let's look at some potential solutions for this. So what are some potential solutions here? So here's the code without any protection. Notice I've kind of highlighted the critical sections of these lines here and here. So we want to find a way to do this. So one of the ways you might think of is like, well, let's make them take turns. So rather than having the entry gate and exit gate just willy-nilly decide that they're going to access that variable, let's make them take turns accessing it. That seems fair. So here's what we added to the code. The stuff that's highlighted is what was added to the original code. The critical sections, you can see, are still down here. But what we did is I made this new variable, and I said which process's turn is it? Is it enter's turn or is it exit's turn? So what I did is I said, okay, I'm going to start off the turn. It's the enter gate's turn. We're making them take turns. So we're saying, hey, enter gate, it's your turn to use the critical section. So what happens is when this runs, if it says, if the process is turn, and for some reason it seems to have deleted the underscore in there. Here, let me fix that real quick. Okay, well, it's there on this version when it's not in the thing, but all right, whatever. Just note that there's an underscore here that's not showing up for some reason, and there it's not showing up, but those are there. Should look like that. I am not entirely sure why it's not showing up. Okay, anyway, this process turn variable, we're saying, hey, if it's not my turn, I just sit here and wait in this while loop until it is my turn. And then when it is my turn, I add 1, and then I set the process turn to the other guy. After I'm done, hey, now it's your turn. So it's kind of like I took a turn, now it's your turn. And the exit gate is doing the same thing. He's just saying, while it's not my turn, wait. And once I get to use this, I set it to be the other guy's turn. So the question is, does this enforce mutual exclusion, and does it solve our problem? So again, you might pause it here and take a look at that, see if you can think through what effect that additional code has. So first question, does it enforce mutual exclusion? And second question, does it solve our problem? So does it enforce mutual exclusion? Yes. But does it really solve our problem? No. So the question here is why not? Why doesn't that solve our problem? And the reason being is because we wanted to have mutual exclusion only one at a time ever in the section. It guarantees that. But here's the problem. Imagine the enter gate runs. He says, okay, it's my turn. So I go ahead and access this, and then I set it to the exit gate's turn. But then another person tries to enter. If that other person tries to enter, the enter gate clicks again. It says, well, now it's the exit's turn, so now we're stuck here forever. So it can't count that person coming in until somebody leaves. So this would allow one at a time access to something, but it does not allow us to have something like a count like we want. So in other words, this one forces alternating behavior. You have to enter, and then you have to exit, and then you have to enter, and then exit, and then enter, and then exit, and enter, and exit. You can't have enter, 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 exit, exit, exit. It has to be enter, exit, enter, exit. So the problem here, it forces them to alternate which one gets access to the critical section. And that doesn't suit our problem very well. All right, so let's move on to attempt 2. So attempt 2 here, the idea is to use a flag variable and only allow entry when it's cleared. And that might seem to make sense. Like you'd say, all right, what I'm going to have is I'm going to have like a variable, think about like a little flag, and before somebody goes inside, they're going to look at the flag and they're going to say, is the flag down? If the flag is down, they're going to say, I'm going to raise it, I'm going to go in the critical section, and then I'm going to put it down when I'm done. So in other words, you can think of it like I don't know, the little, if you look at a bathroom door and it has a little red and green thing, occupied, unoccupied, you can think about it like that. So you look at the thing and says, it's unoccupied right now. So I'm going to go ahead and set it to occupied, enter the critical section, and then when I leave, set it back to unoccupied. Now you might think that would work. So first off, does it enforce mutual exclusion? And does it solve our problem? And the answer is no, it doesn't enforce mutual exclusion. It also does not solve our problem because our whole problem was to control access to that critical section. So why not? And the problem is that if these are running concurrently, they could both look at this while process inside equal true. And let's say it's false right now. So let's say both the entry gate and exit gate hit that line of code at the same time, where they both look at the flag. They both say nobody's inside. They both then continue on after the while loop, and they both say I'm inside. And then they subtract or add to the count, access the critical section. When they leave, they both set it to false, but they were both still in there at the same time. So both of them, because the flags can be checked simultaneously, both of them can enter. So we've really just moved our critical section to now include this, that we now shouldn't check that because we have a delay of time between when we check it and when we set it. But these can't be interrupted now either. All right, attempt 3. Well, maybe we're onto something there with this flag idea. So let's try it a different way. Let's use 2 flag variables, 1 for each of them, because we might say, well, them sharing that flag between them was the problem. And again, ignore the missing underscores. I don't know why the presentation software is doing that. It looks like it's overlaying part of this too. It's probably the highlighting on there is causing a problem. But now I have 2 flags. I have one for P1. He has his own flag that he can raise. And then P2 has its flag that it can raise. So now what happens is we're raising the flag now before we actually check the other guy's flag. So in other words, I'm going to raise my flag and say I want inside. And then I'm going to look at the other guy. And if he doesn't want inside, it's all clear. So in other words, if we both don't want to go in, everything's good. And I can go ahead and do my business. And then I can put my flag down when I'm done and say I no longer want inside. And on its surface, this seems like it might make sense. It seems like we put up our flag first because in any effective ordering, they're both going to have done this, even if they're running at the same time. And I see a typo here. Let me fix that. Hold on. I don't know why that said false. Okay. Okay, so they both want inside. If they both want inside and both have their flags up, or whichever one got there first will have its flag up first. But here's where the problem comes in with this. Well, first off, does it enforce mutual exclusion? Yes, it does. Does it solve our problem? No, it doesn't. And here's why. If both of them hit the line of code where they're setting their flag at the same time, which now I've got to fix this one too, hold on. So if both of them set their flag at the same time, and then they both then proceed onto the while loop, and they look at each other's flags, now they're both stuck there waiting for the flag to be something other than true, and it's never going to be because they're both looking. In other words, they said, I want in, I want in. Do you want in? Oh, he wants in. I'm going to wait. Yeah, they're both waiting on each other. So this is a condition that's a form of what's called deadlock, and in this case live lock, because they're in this active loop running here, consuming CPU resources, waiting on some event that's never going to happen because they're waiting on the other party. And they're just going to wait there forever. They're just going to sit there and wait on each other forever. And we're going to look at deadlock and live lock and other liveness property violations later on in the semester. But note that this is terrible. We've now not just gotten a wrong number out of this, the wrong number of people inside at the end of the day. We've now completely locked up the system. It's stuck. Nobody now could enter or exit because the whole thing is locked up. Different kind of problem, but still a problem. But nobody will ever get into the critical section 2 at a time, so we won't ever get wrong answers or wrong numbers out of this. But we might not ever get any answer, any number, because it could lock up. All right. Attempt 4. We're going to use 2 flag variables again. This is kind of a modification of the one we just did. And in this case, though, we're going to set the flag before entry, but we're going to clear it while we wait and then restart while we wait. So the problem you might think over here was that this one said he wanted inside, and then while he was waiting, he kept saying he wanted inside, which never would give the other one a chance to move forward. So you might think, well, you might think of it like this. You go to get the bathroom key to the gas station bathroom, and if 2 of you have the key, you look at the other guy and said, oh, well, he has his key and I have my key, so we're just both going to wait. So you might say, if you go to the bathroom and you see somebody else waiting there that also has a key, you put your key back. And then you try again in a little bit. So let's look at that, how that code works. In other words, we assert our flag, and this apparently inherited that same typo, which probably means it's on the next page. I'll have to fix it on that as well. So we both want inside. We then say, well, if the other guy wants inside and I want inside, then I'm going to wait. But while I wait, in this loop, I'm going to put my key back. I don't want inside while I'm waiting. The other one doesn't want inside while it's waiting. And so now we have this situation where one of them is put, when he looks at this while loop again, we'll see it when the other guys put it back, and he'll be able to proceed and get into here. Now we're getting close to being onto something here. But that does enforce mutual exclusion. It will not lock up in the traditional sense, but it has another problem. So does it solve our problem? It might seem to at first, but there can be another problem here, and that problem is a different sort of problem. And the problem being that they both grab their, raise their flag, they look at the other guy, see his flag is up, and they put their flag back, they wait a little bit, and then they both acquire the flag again. So the problem here is that they could, in sync, because we can't make any assumptions about the timing, they could be synchronized with looking at each other, putting the key back, looking at, or waiting, waking up, grabbing the key, looking at each other again. So they could keep putting it back, getting it, looking. Still has it. Put it back, get it, look at each other. Still has it. Put it back, get it, look at each other. And that could just go on forever, or some indeterminate amount of time. And so there's no guarantee that they'll ever actually get into that critical section. They could sit there forever acquiring and releasing their flag, trying to get into that critical section and never make any progress if they remain synchronized. And it could be like a really long time, and then they get out of it. But either way, this is not considered a solution to the problem, because it could cause what's called starvation. In other words, they're not holding on to something, waiting for something that will never happen. They're just holding on to something, waiting something that isn't happening because of statistical reasons, or timing reasons, or probabilistic reasons, or something like that. So this is a different phenomena, kind of related to the live lock that we saw in the previous example, but this is called starvation. And maybe you've seen this from your previous operating systems class or talked about it, but here it is in practice. And well, let me go back for a second. There are some ways to make this better rather than sleeping this the same amount of time. We could sleep like a random amount of time. That might help make this so that they don't starve like that. But there's still a possibility that you could go on for a little while. They both get the same random number. They both acquire the flag at the same time again. And it will take several iterations before they get out of that. So let's look at one where there is a guarantee of success. Now this one is called Decker's algorithm. And my face is covering up just the word algorithm there, so don't worry too much about that. So there you go, Decker's algorithm. And what Decker's idea was to use something similar to what we did in attempt 4. But instead of that putting the flag, or lowering the flag while we wait, his idea was we'll make a tie-breaking possession error when they get there at the same time. In other words, if both of them get there at the same time and they both are wanting access to that critical section, then we have this kind of possession error that says who gets to go first. And then we trade that off just like a possession error in basketball, that essentially if they get there first, process 1 says, oh, I have a possession error, I'm going to go, you're going to wait. And then when process 1 is done, he gives a possession error to the other guy. So the next time there's a tie, the other guy goes. So that makes it completely fair. So does that enforce mutual exclusion? Yes. Does it solve our problem? Yes. And let's take a quick look at what happens. So in other words, they both, and again, I've got the same typo that got rippled through here. Oops. Let me fix it. And I get it over here. I probably got one more I'm going to have to fix here too. Okay, so Decker's algorithm, they both start out not wanting inside. P1 raises his flag before he checks anything. He then waits while the other guy wants his flag. He lowers his flag, but then he looks at it and says, okay, who has a possession error? If the favored process is the other guy, then I wait. And while I'm waiting, I've lowered my flag, which will allow the other guy to proceed. And afterwards, I raise my flag back up again after I'm done waiting. And then I check to say, hey, does P2 still want inside? In this case, that'll eventually be done because when this one's done, P2 asserts that he no longer wants inside. And then I'm allowed to go. And then after I'm done, I make sure that the only way that I could have gone if there was a tie was if the possession arrow was pointing the other guy's way. But now I know it'll be pointing mine because he put it back to me. And then I'm going to put it back to him. So in other words, once I've had a turn, I give the other guy the possession arrow. Once he's had a turn, he gives me the possession arrow. And that's this favored process variable here. And that's thanks to a mathematician, Theodorus Decker. And that's the first recorded solution to the concurrent access, mutual exclusive access problem that we saw in this ornamental garden problem. All right. Now, another solution here is called Petersons algorithm. And Petersons algorithm, the way that it works is essentially like Decker's algorithm, but a simpler version. And there's no reason to ever lower the flags and raise them again. So notice the code is smaller. It's done away with that. Put the flags down, raise them again. Put them down, raise them again. And the way it's done that is basically, it's the same kind of concept, but let's trace through this. So P1 states that he wants inside. The favored process, he sets the favored process to the other guy. He says, I want in, but you can go first if you're there at the same time as me. And then it enters this while loop that says while P2 wants inside is true, and the favored process is the other guy. So if the other guy wants inside and he is the favored process, which I just made him the favored process, then I'm going to wait. And so notice that since this is an and, both of these have to be true. As soon as I'm the favored process, I could unlock and go, or as soon as he no longer wants inside, I'm going to unlock and go. Eventually, I'll get access to this critical section. And then when I'm done with the critical section, I'll say, hey, I no longer want inside. So notice I never had to lower my flag. And the key to this one is this while loop with the and in here. And the fact that I set the other guy to the favored process up front. So one or the other, that favored process variable either has to be a 1 or a 2 when we hit this while loop down here. Because remember that we have the interleaving, it's either got set to a 1 or it's got set to a 2. It has to have one of those two values in it. So when I get down here, if it's 2, if it's the other guy, then I wait. If it turned out to be 1 and we came through, then he waits and I go. So very clever, very simple. So does it enforce mutual exclusion? Well, it's got Peterson's name on it. It's called the Petersons algorithm. Pretty simple algorithm. But yes, does it solve our problem? Yes. And this one is thanks to a computer scientist named Gary Peterson. This is a much simpler solution than, more elegant solution than Decker's algorithm, where you're lowering the flags and raising them over and over again. And you can kind of see that distinction in how much simpler the code is. I raised the font size changed, but you can see there's a lot more lines of code there for Decker's algorithm than for Peterson's algorithm. And this one is also easier to adapt to more than 2 processes than Peterson's algorithm is. And I'll let you think about how you might adapt that to more than 2 processes. And you might think that this stuff was ancient history, and maybe to you it is, but really it was somewhere around C language had existed for about 10 years before Peterson came up with this Peterson's algorithm. So we're talking somewhere in the early 80s. All right, so enforcing mutual exclusion, what we've shown today is a couple things. The first thing is we've shown that it's possible to solve that mutual exclusion problem using just software, no hardware, no special operating system, API calls or anything like that, just some shared variables and just some software. But it's also, the other thing we learned today was anytime we have concurrent processes writing to a shared variable or some sort of shared memory, then we're going to have this need to be careful. We have critical sections there. We have to watch out what we're doing. And sometimes even just reading data as it's being updated has to be protected. And that's a case that we didn't look at in this example. But if there was just one of them changing the data and the other one reading the data, there's a possibility of corruption there. And the reason is this, that if you're on, let's say, an 8-bit system that transfers data from the processor to memory 8 bits at a time, and let's say you have a 16-bit, let's say it's like a short in C language. It's 2 bytes, it's a 16-bit number. Well, when that memory goes to get updated by the code, it's going to get updated as the 2 parts, the most significant byte, well, for you, the most significant byte, and then the least significant byte. So it has to put those in, move the high part of this to memory, move the low part of this to memory. And it has to do that because we're dealing with an 8-bit processor with an 8-bit wide bus. It can't move 16 bits across an 8-bit bus without breaking it up into 2 operations. The same thing might happen on a 32-bit system. You have a 64-bit number, like a long type, and you're on a 32-bit compiler that compiled it for 32-bit instructions. How do you move a 64-bit number into memory on a 32-bit bus? 2 sections at a time. The first half, the second half. Well, if you've only moved half of that, and then the other one reads that value, now we have a number that's half of the old value and half of the new one, and we have something that's been corrupted. And that especially gets weird when you're dealing with things that are like 2's complement, where negatives have all the bits set, including the sign bit. So -1 is essentially all 1s, where 0 is all 0s. So if you have something that's hovering around like 0, -1, 1, -1, 0, it's like some sensor value and it's being updated as 2 parts, you might get something where if I update the first part of it to be 0, all 0s, and the second part to be all 1s, this is with a 16-bit number, I'll have essentially 255 pop out. So even though the value should be around 0, I'll have 255, or I'll have like some -256, and I'll have, as it hovers around 0, you'll have like 1, 0, 255, you'll see like a spike in the data, -256, 0, -1, 1, 0, -1, 255. So you'll get these erroneous values because we need to lock that while we update it and then unlock it, because otherwise we'll have a mixture of old data and new data when we read it. So in other words, we need to be careful anytime we have some kind of shared memory between multiple processes. We need to make sure that mutual exclusion is enforced, or the data can either be corrupted as it's stored in memory or corrupted as we read it. Now, there are other constructs that achieve that mutual exclusion that we looked at in here. And we're going to see those later in the semester. We're actually going to look at several of those later in the semester. But for right now, Petersons algorithm, Decker's algorithm, both really useful to know those software solutions. We're not going to be using those a lot other than for to do a little test in the lab coming up. But note that there is the possibility of creating a software-only solution that doesn't require any kind of API or construct or data objects or anything like that. But it turns out, since this is such a common problem, that there are a number of most languages that support concurrency in some way have constructs that allow us to control that without having to do it through software, like pure software like we have here. Okay, next class what we're going to do is we're going to start writing some concurrent code. We're going to have a lab. The language that we're going to be using in here is Python. So if you are not familiar with Python, I'd suggest you start looking at it. I'm going to post a quick or a brief Python getting started guide, or it's not like a textbook. It's like an 8-page document that shows how to do different things in Python. You can use that as a reference. It does not show how to do any of the threading stuff. It's more basic language features. But if you've programmed in another language, you should pick up Python pretty quickly. It's a easy to learn language, but also very powerful, very expressive. A lot of really cool built-in things that make things easier than maybe in some other languages. And it's also very concise, unlike some other languages. So it'll generally take about half to 1/10 the amount of code to do something in Python that it would take to do it in something like C++ or Java. So we're going to use Python in here, at least initially. Later in the semester, we'll probably look at some concurrent programming in other languages like C, C++, maybe C#. But that'll be later in the semester. But for the time being, initially, we're going to be using Python to do some things. So that's what we're going to be doing next class. Okay, so that's all for today's lecture. Make sure you've done that lab 0. If you haven't, I don't want you to lose points for something silly. And then next week, we're going to have another lab. So everybody stay safe, wash your hands, wear a mask if you're out and about around other people that aren't from your household. And if you need anything, email me, give me a call, send me a text message. If you need an appointment, let me know. We'll set up a Zoom meeting or come down and meet face-to-face. You got to let me know, though. So I'll see you next time.